Thank you very much. This is my second slide, but anyway. We have heard in the last talks of the importance of random numbers, and let me stress it once more in the setting of quantum key distribution. So this is a continuous variable quantum key distribution system, and it's a prepare and measure system. So we need to generate random numbers with a generate coherent states by randomly modulating with a modulator, and we need random numbers for these. And the randomness of these random numbers is super important, because if they are not random, we can not do quantum key distribution. So what we need is certified security of these random numbers. We need to trust them. But we also need that they are unpredictable, that they are private, that nobody else knows them. And we also need fast real-time generation. So the randomness certification is one of these parts. So how can we make sure that these are really random? And we already have heard about device independence. Device independence is nice because it introduces the lowest amount of assumptions, but it is also only generating random numbers at very low speed. But we want to do a high-speed QKD. So what we can do is we introduce more assumptions. And one idea is to introduce assumptions on the detector only. This is what Marco will talk about. Or we also introduce assumptions on the source itself, and this is what I will talk about. So I will talk about a device-dependent random number generator based on vacuum fluctuations, and Christoph this morning in his tutorial has introduced vacuum fluctuations QRNG already. So vacuum fluctuations, also called shot noise, that's how we called it. And our system is basically a homodyne detector using a laser as a reference, split at a 50-50 beam splitter, detected by 2 pin photodiodes, subtracted, and amplified with a transimpedance amplifier. Then we somehow need to sample those, so we need maybe some conditioning, and then an analog to digital converter, which in our case is, has 1 gigasamples per second with a resolution of 16-bit. And then we need to do randomness extraction, and we use a randomness extractor, an information theoretically secure one, tuplets hashing, which we implement in real time on an FPGA and reach a real-time generation of 10.67 gigabit per second, real time. This is how our detector looks like. This is how our FPGA looks like. Now, we measure a lot of samples, and we calculate the power spectral density of it, and then it looks like this. And if we calculate then the autocorrelation, we see, okay, the samples are not independent of each other, but we have correlations in time. And this is a problem, and many security proofs for device-independent QRNGs have not taken this into account, but what they try to do is somehow to make these samples independent. But what we do instead is to take this in the security proof into account, so that we don't have to do any post-processing before we do randomness extraction. Okay, so the idea, I just have time to roughly give you an idea of how this works in the security proof, but the idea is to map the non-iid process, which we have here, into an iid process, and we do this by using the entropy rate and using the power spectral density, which we have up here, to calculate the conditional variance. The conditional variance is basically then the variance of the virtual independent process. So if I have an iid process, the conditional variance is actually exactly the same as the variance itself. Otherwise, it's lower. Our proof has 3 parameters. That's the variance of the signal, the conditional variance of the signal, and the conditional variance of the excess noise. The signal means basically we measure everything. Excess noise is everything which is on top of the vacuum fluctuations. We need to characterize all of them, and as we want to trust them, we need to do that in a way that we can afterwards be sure that we did it in the right way, that we're really extracting random numbers only from vacuum fluctuations and not from excess noise. And we do this by introducing confidence intervals in our measurements, and then take the min entropy, the minimum min entropy within the confidence intervals. So for the characterization, the variance of the signal and the conditional variance, this is simple, because we are just calculating both from the power spectral density. So we just need to measure a lot of samples, calculate the power spectral density, and can write down the confidence intervals also for that. So this is relatively simple. What is more complicated is the variance of the excess noise. So this is how it in the end looks like. This is the power spectral density of our signal. This is what we had before. And then we estimate, okay, what is the amount of vacuum fluctuations? And this is on this. And as you know, we need I say in a second how we get to that. So if we have the power spectral density of the vacuum fluctuations, we can just subtract it from the signal and get the power spectral density of the excess noise. The vacuum fluctuations are given by the Schottky-Schott noise. Okay, this gives us the power spectral density, but it's flat. But our detector has a certain response, so we need to measure the response, and not only of the detector, but also of the acquisition system, including the ADC. And we do that by introducing into the normally vacuum port a second signal laser and look at the beat frequency of these two lasers. It has a certain amplitude, and then we sweep the frequency of the signal laser and register the amplitude for each individual frequency difference to get the transfer function. And if we combine these measurements, which together with the vacuum fluctuations, we end up with a formula that is basically this. H bar omega L is the quanta of Schott noise. TF is the transfer function, basically the measurement which comes out here, divided by the signal power. So we need to measure the signal power, which is probably given by a systematical error. And by this, we can then estimate what the vacuum fluctuations are. What I assumed here is that the visibility of this measurement is 1 and that the quantum efficiency is 1. Very crude estimation, but it gives us a lower bound without measuring these two numbers. If we would measure them, the vacuum fluctuations would basically go up. So this gives us a lower bound, which makes it a little bit better. And then, to summarize, by using this model with non-iid samples, we get a min entropy of 11.4 bit out of our 16-bit measurement. And we perform then real-time extraction on the FPGA of 10.67 gigabit per second. We do a metrological characterization so that we can be sure what the amount of randomness is with an epsilon of about 10 to the minus 12. And this gives us random numbers with an epsilon given by these three contributions. So we have the contribution of the parameter estimation I just talked about, and then also the epsilon of the leftover hash lemma, which is growing in time. If an adversary registers all the site information he gets over time, and then also the epsilon of the seed. So we chose values here for the epsilon hash in this case that this random number generator can run for about 10 years. But what is a little bit open is how to get a good seed. And I think this is right now at least the biggest challenge. And I'm very open and be very glad about discussions about that. And so basically, how do you get the seed, and how do you can make sure that the seed is random? And Then to conclude, so this is a random number generator that we can use for CVQKD. It's fast enough, maybe for a 100 megabyte per second system. What we need to do is to do a bit of online testing and power on self-tests and integrating it into a package, and then we can directly use it. Thank you very much.